do is I'm planning to look into this low rank approximations again and give a little bit of geometrical intuition about these low rank approximations, and we will see how these low rank approximations come into the picture and why are they really very important, so to speak, and what really is happening. Okay, so why these things are really important, why these things are important. So that's what I really want to tell today, and from next class onwards we'll continue with several other different types of low rank approximations, and tensors. We'll look into tensors and we'll see how those tensors are also really very useful. Okay, and these matrix decompositions, low rank matrix decompositions that you see, they will also be really very useful in some neural network applications. Okay, so some interesting things about these I will state today, and based on all these things you will realize the importance of these low rank approximations. Okay, so what I really want to look at is low rank approximations. So I think Adhay already covered singular value decomposition, and based on singular value decomposition he has already taught in the class principal component analysis and these low rank approximations, right? What these low rank approximations really mean. So I think Adhay has already taught you that. So given a matrix A, you can write down A is equal to U sigma V transpose as its SVD, right? Singular value decomposition. So these V are right singular vectors, left singular vectors, and singular values. I think that is something that you have already understood. One connection I just want to tell you, of singular value decomposition with the geometry that we have already seen is that this singular value decomposition has a relation with this maximum magnification and minimum magnification, so to speak. Okay, so suppose matrix A is a matrix of the size 2 by 2, then you do this singular value decomposition U sigma V transpose of this particular matrix, and what you really are looking at is that how this actually changes to a ellipse, right? So this singular value decomposition geometry is really very interesting. So this is your major axis and this is your minor axis, right? So let me use a different color. So this blue that I'm showing here is your major axis direction, and this is your minor axis direction. And what is the magnification is what you are looking at. Okay, so this A is equal to U sigma V transpose, you can write as AV is equal to U sigma, right? So you can write this as AV is equal to U sigma, and which really means that AV1 is equal to sigma 1 U1 and AV2 is equal to sigma 2 U2. Okay, and what these V1, V2 really are saying is that these directions V1, V2 here are the directions which are these directions orthogonal V1 and V2, and let us say this V1, A times V1 actually gets mapped to this sigma 1 U1, and this other thing A times V2 gets mapped to sigma 2 V2, right? So this U1 and U2, so this U1 is actually the direction of maximum magnification, and this U2 is actually the direction of minimum magnification. Okay, so you have this direction of maximum magnification and minimum magnification, and these lengths, so this length is basically your highest singular value sigma 1, and this length is basically sigma 2. Okay, this is what your singular values are really. So the singular value decomposition is actually completely telling you, you look into the domain. So domain is this unit circle that you have here. In the domain, you know which two vectors V1 and V2 are there orthogonal. So a singular value decomposition is going to tell you that. So this V actually is the vectors in the domain, and u are actually the vectors in the range, and sigma are their magnifications actually. So when A acts on vectors vi's, v1, v2, v3, v4, and so on and so forth. So you have a unit circle, and how that unit circle gets distorted because of action of A, that is what we are really looking at. Okay, so this is actually action of A, and that is what we are looking at through this singular value decomposition. So geometrically, this is what is really happening. So you pick those v1 and v2 through singular value decomposition, act A on it, and then you go into the directions of maximum and minimum magnification u1 and u2, and how much is the magnification really happening in the direction of u1, and how much is the magnification happening in the direction of u2 is actually given by the scalar sigma 1 and sigma 2. So if you have an orthogonal matrix A, which is R2 by 2, then you know that the circle, unit circle goes to a unit circle. And obviously then sigma 1 and sigma 2 are both equal to 1, right? So that is something that we already understand. So this is what this singular value decomposition geometrically is really telling you. So it is basically telling you, so this u1, the first singular vector, actually is the direction in which maximum magnification happens. And suppose R is the rank of the matrix, then there are R singular values which are non-negative. Exactly, and the remaining singular values are 0, and the remaining are all positive, right? Our singular values are positive. That is what you have. So what is really going to happen is that you have to visualize this picture in n and m dimensions, right? So if a matrix A, so generalize this. So suppose I take n is equal to m is equal to 3. So suppose I still have r is in r3 by 3. Then what is going to happen? You have a three-dimensional space, and then you have a unit sphere here, right? So you have a unit sphere sitting over here, and this unit sphere is going to get transformed into an ellipsoid, right? So this is the ellipsoid that basically you will be having. I cannot really draw an ellipsoid here. So you all have to now start visualizing this. And when you draw this particular ellipsoid, what is going to happen? So this ellipsoid will have three principal directions, right? So here this ellipse had two principal directions. We call them major axis and minor axis. So similarly, like a major axis and minor axis, which are orthogonal to each other, this ellipsoid is going to have three principal directions, so to speak, right? So those three principal directions are actually u1, u2, u3. So u1 is the direction where maximum magnification is going to happen. So you have an ellipsoid. So in the first direction, that is what is going to happen. Then orthogonal to that direction, you will have a plane. On that plane, you will have an ellipse again. And in that ellipse, the u2 will be the direction. So on that plane, what is the maximum magnification? That is in the direction of u2, and you keep on doing this, right? And u3, obviously, the last one will be the minimum magnification. So the magnifications in orthogonal directions in descending order is what this u1, u2, u3 is going to do. And now you generalize this further in m and n arbitrary, and then you realize when you have this arbitrary, you will have a unit sphere in n dimension. That unit sphere in n dimension goes to a an ellipsoid in m dimensions, and those things that you see here, they really are really very important, right? And then from this, once you understand this, then the smallest singular value here is actually the minimum magnification. And then once you understand this relation, then you know why the singular value is equal to the rank of the matrix have to be non-zero, right? Because suppose, for example, in a 2 by 2 case, if sigma 2 is equal to 0, then if sigma 2 is equal to 0, then what I'm saying, I'm really saying that V2 is going into the null space, right? V2 belongs to the null space or kernel of this matrix A. So you have a non-zero vector in the kernel. That means that matrix A is losing rank, right? So that is what is really happening. So this sigma 2, if one of the singular values is 0, then this ellipse actually collapses into a lower dimensional ellipse. So here in this particular example, what is happening? If sigma 2 happens to be equal to 0, if sigma 2 is 0, then you will have only a straight line of length 2 sigma 1 in the direction of u1, right? So you will have a degenerate ellipse, or you will have an ellipse in a lower dimension. So the dimension is actually one dimension here in this particular case. So that is why this is something that is really very important. And now you think of it, so what is happening in principal component analysis geometrically again? So what is really happening? Suppose A is a data matrix which is of the size n by 2. Okay, so suppose A is a matrix of the size n by 2. So this n, what is really happening? N by 2. Okay, so these are attributes, say for example. Okay, so these attributes are like, let us say, height and weight. Okay, so if these are the attributes, then each row here represents the observation on an object, right? On a subject, right? So I will measure the height and weight. So height and weight of person P1, then height and weight of person P2, and so on and so forth, right? So now you know that height and weight are highly correlated. Maybe if there exists, okay, so if there exists a relationship, weight is equal to alpha times height, okay, for some unknown alpha, and now this epsilon is coming into the picture, which is measuring inaccuracies in the relationship. Okay, so approximation that we are making. So in an ideal situation, if epsilon is equal to 0, in an ideal situation, if you take epsilon to be equal to 0, then what really happens? What really happens in that particular situation when epsilon is equal to 0, this column, which is nothing but the weight column, so this particular column becomes a linear multiple of the first column, which is nothing but the height column, right? So what does that mean? That means that the rank of this matrix is actually equal to 1. If the rank of this matrix is really equal to 1, what is going to happen geometrically? What is going to happen geometrically? A is a matrix which is of the size Rn by 2. Correct? A is a matrix which is of the size Rn by 2. So can you tell me from where to where this linear map is acting? From where to where? Can you tell me? A is a linear transformation from where to where? It's a linear transformation from R2 to Rn, correct? So it's a linear transformation from R2 to Rn. So what is it going to do? It is going to take a unit circle in R2 and going to transform this unit circle into an ellipse in an n-dimensional space, correct? So you have an n-dimensional space, and in that n-dimensional space you are going to have maximum an ellipse, right? It's not going to be an ellipsoid, because maximum the rank this matrix can have is rank 2. So you will have a two-dimensional subspace here. So you'll have a 2D subspace here, and in that 2D subspace, so two-dimensional subspace that you have here, in that two-dimensional subspace, on that two-dimensional subspace, you will have the ellipse. Okay, so that is the ellipse that you are really looking at. So this is a geometry that you have to understand. And now if the rank of this matrix is 1, then in that two-dimensional subspace, the ellipse that you have drawn, that ellipse is no longer an ellipse, but it's actually a straight line, right? So that is what is really going to happen. That is what is really happening in this particular thing. And that particular line, that particular direction, U1 direction that you see, actually that direction is the direction of the principal component, right? The first principal component. And U2 is the direction of the second principal component. Geometrically, that is what you have as your geometrically, that is what you have. So these U1, U2 are projections onto that dimensional space, and corresponding V1, V2 here are actually what you call the matrices, right? So weights, you multiply A by V1, then you get the first principal direction, and so on and so forth. So basically what you are doing, you are trying to find out the best linear combinations, right? So you are looking. So that's what you are doing here really. So that is what principal component analysis is doing. Okay, so this is the geometry behind PCA, and this is what really happens. And this epsilon almost always is not equal to 0. So when this epsilon almost always is not equal to 0, because there is a very high correlation between weight and height, that epsilon is very small, and the ellipse that you will see in this n-dimensional space. So in that n-dimensional space, you have a two-dimensional subspace. In that 2D subspace, you will see an ellipse. The ellipse will be almost degenerate ellipse, right? So if the columns are almost linearly dependent, then the ellipse is almost a degenerate ellipse. It will almost look like a line segment, right? So that is what pictorially is really happening. That is the geometry behind this thing. Is this okay? Do you understand what I'm saying? Any doubt here? Any comment that you would like to make? Okay, so moving further.
Sir,
Yes. Yes.
sir, can you once again repeat the direction of PCA, first PC?
So see what is going to happen. You have a matrix A. The matrix is going from R2 to R2 to Rn. Do you understand this part, Puneet?
Yes, sir.
Yeah, so every vector in R2 here, so there is going to be a V1 and V2 here. So suppose this is V1 and this is V2. Okay, these are the columns of matrix V. So A is equal to U sigma V transpose, right? So I am looking at AV is equal to U sigma, right? So what I am really looking at is A1 is equal to this and AV2 is equal to this. That's what I am really looking at. Is that okay?
Yes, sir.
Puneet? Yeah. So do you agree that V1 and V2 are vectors in R2? Do you agree?
Yes, sir.
And U1 and U2 are vectors in Rn. Is that also clear?
Yes, sir.
Yeah. So now if you look at span of U1 and U2, if you look at span of U1 and U2, so the span of U1 and U2 is a two-dimensional subspace of Rn. Is that clear to you?
Yes, sir.
So U1 and U2 span is actually a two-dimensional subspace of Rn. And in that two-dimensional subspace of Rn, you have a U1 direction and the orthogonal U2 direction to U1. Can you visualize that?
Yes, sir.
Yeah. And now what is happening to this unit circle? This unit circle is getting mapped as an ellipse in this subspace span of U1, U2.
Yes, sir.
Yeah. And how is that ellipse looking like? The way this ellipse is looking like, U1 in the direction of U1, you have maximum magnification. In the direction of U2, you have minimum magnification. So U1 is the direction of the major axis and U2 is the direction of minor axis.
Yes, sir.
Is that fine? So this U1 basically, U1 direction basically is having maximum magnification. So if sigma 1 is really bigger than sigma 2, that means that I have a very high condition number for this matrix, sigma 1 by sigma 2. If the condition number is really very high, then can you imagine that the major axis length is really very big than minor axis length?
Yes, sir.
So the ellipse that you are looking at in this two-dimensional subspace, it's almost going to be a line segment with length 2 sigma 1 in the U1 direction.
Yes, sir.
Yeah, so this is what is really happening. So if now you go back here and you think of it as if this matrix A, which is Rn by 2 matrix, is a data matrix. Okay, this is a data matrix. What is the data? The data is each row is an observation. Each row is an observation. And what are the observations you are making at? You are making observations on two attributes. Here I am taking two attributes to be height and width. Is that okay?
Yes,
And
sir.
I know that height and weight are very highly linearly correlated, meaning that there is a linear relationship of this type. Okay. So if this linear relationship is such that weight is equal to alpha times height exact, then I know that the rank of this matrix is 1. because
Yes,
one
sir.
column is a linear multiple of the
Yeah.
other column. But in
Yes.
reality, this relationship is not exactly linear. Okay, it's almost linear. So that almost linear and exact linear, there is a difference, right? So there is some error. So that error I am putting inside this epsilon. Okay. Because of this epsilon now, do you agree that the columns are not linear multiple of each other?
Yes, sir.
So from linear algebra point of view, rank of this matrix is 2.
Yes, sir.
But what is your intuition saying? Your intuition is saying is that if this epsilon is really very small, if this epsilon is really very small, then what is happening? The columns are almost linearly dependent on each other, or the one column is almost linear multiple of the second column.
Yes, sir.
Yeah, so this almost linear multiple or almost linear dependence, if you remember long time back when we were talking of this maximum and minimum magnification and condition number, you remember we had discussed this concept. So if the condition number is really very high, then the columns are almost linearly dependent. We had actually proved that. You remember?
Yes, sir.
Long back. So here also, if the columns are almost linearly dependent, condition number is really very high. What does that mean? This circle that you see here, when it get transformed into the ellipse in this two-dimensional subspace of Rn, the ellipse is almost degenerate ellipse, almost looks like a line segment.
Yes, sir.
I hope here when you are doing this for everybody, you are recalling the figures that you plotted while you are doing your assignment 2, right? In your assignment 2, there were several figures I had asked you to plot, and there you had like varying different values of epsilons. You saw circles going to ellipses, almost degenerate ellipse, and so on and so forth. So if you have done that really very well, then you can see that you can visualize these things really very well. So now what is this U1? So U1 is the direction where almost all important information about the data is stored. Do you agree, Puneet?
Yes, sir.
Yeah, so that U1 direction is actually a very important direction. That is the first principal component direction. How do you get it? You get it by multiplying V1 on the right of this A. So that V1 you call loadings vector, no? So A times V1 is equal to sigma 1 U1. So that sigma 1 U1 you will have. So that U1 unit direction A V1 is actually the first principal direction. If sigma 2 is equal to 0, if sigma 2 is equal to 0, then you have only one principal direction. If sigma 2 is not equal to 0, but it is really very small, then you are saying that the information in the direction AV2, which is nothing but U2, is not much, right? That second linear
Yes, sir.
combination A times V2 is not really playing a role. That's the geometry basically that you see behind this singular value decomposition and principal component analysis. So basically, when you are looking at principal component analysis, what you really are looking at, even if A is a data matrix, you think of it as a linear operator from R2 to Rn, and when what is it doing to this circle? Says that the columns were orthogonal, then unit circle will go to a unit circle, and then you have both the directions U1 and U2 really very important directions, because the magnification in U1 and magnification in U2 both are 1. They are almost same, right?
Yes, sir.
But in the case when condition number is really very high, the case when condition number is really very high, you know that the columns are almost linearly dependent. And when you say the columns are almost linearly dependent, you can use n minus 1, for example, linearly independent columns. In this particular case, we are talking of orthogonal columns U1, U2, Un minus 1. So you can have U1, U2, Un minus 1 orthogonal columns, which will approximately span the same space as the column space of it. Do you agree?
Yes, sir.
So that approximate spanning that you are looking at U1, U2, Un minus 1 by neglecting the smallest singular value sigma m, that is what is basically the principal component subspace. So here in this particular simple case, if sigma 1 and sigma 2 only two singular values are there and sigma 2 is really very small, that means that you are looking basically at a line segment of length 2 sigma in the u1 direction, right? So all the vectors on the circle are getting roughly mapped into this line segment. Do you agree?
Yes, sir.
Yeah. So if I just take U1 and I neglect U2, then will you agree with the fact that the span of U1, which is nothing but that full line which is passing through origin, one dimensional subspace, is roughly equal to the column space of the matrix A?
Yes, sir.
So that subspace that you have computed, which is U1, is actually the principal component subspace, right? So here what it really means, you have actually found out the linear combination between height and weight, that particular linear combination, which will, which will be in that direction. Correct. So that V1 that you really have here is the linear combination of columns of the columns of these vectors. So that V1 when you multiply on the right hand side, the loadings vector when you multiply on the right hand side of this matrix A, when you do that, then you will get the first principal direction, means that the most important direction. And in this particular case, if we neglect the second singular value, that's the one dimensional subspace which approximates. So that's the dimensionality reduction you have achieved. Here you have two dimensions. One is height, one is weight. And now what you have done, you have found out a linear combination of these two dimensions, height and weight, and you are only looking at that dimension, one dimension, which is nothing but the direction of u1, and you are saying that whatever this matrix is talking about. So what is it talking about? So when we see this matrix, it is going to talk about its column span. So whatever is the column span of this matrix, you will say I am going to approximate very nicely that column span by a one-dimensional subspace. That's what you are really looking. That's what geometrically you are really saying. So what we are doing, we are looking at the column span of A, and how well we can approximate that column span of A basically is what we are looking at, and that approximation is achieved by this principal subspaces. Okay, so that's what we are really looking at. Is that okay?
Yes, sir.
Now does that make sense?
Yes, sir. Got it, sir.
Okay. Yeah. Any other issue here at this point of time? Any other doubt? Any other comment? Okay. So one thing I just want you to kind of appreciate at this point of time is that why these low rank approximations are important. Okay. Why these low rank approximations are important. So first I'll consider the case of n by n matrices. Okay, so consider a matrix A of the size n by n. I'll consider first this n by n case. So A is in R n by n, and suppose A is equal to sigma 1 u1 v1 transpose plus sigma 2 u2 v2 transpose plus so on and so forth, sigma n un vn transpose be the SVD of matrix A. Was this notation of SVD introduced in the class? Did you write SVD in this form? Do you know this? Can you confirm, Puneet?
Yes, sir. Yes, sir.
Yeah, this was done, right? You know how this form comes of SVD. So this U basically columns of U1, U2, UN. Then sigma is basically sigma 1, sigma 2 up to sigma n, diagonal matrix in this particular case because I'm taking n by n. And V transpose basically is V1 transpose the first row, V2 transpose the second row, Vn transpose the last row, right? So you can generalize this to any rectangular matrix with R singular values, and this is how the matrix A I can write. So it's just, so A is equal to U sigma V transpose. I can use the properties of matrix vector matrix multiplication, and using that I can write down my matrix A to be this, right? A1 A is equal to sigma 1 V. So the question that you must have answered, because you have covered this low rank approximation, is what is the nearest rank n minus 1 matrix to A? So can anybody tell what is the nearest rank n minus 1 matrix to A? So you have covered low rank approximations, right, in the last week's classes. So do you remember this? Correct. So this matrix A n minus 1, have you seen this in the classes last week and this week?
Yes, yes.
Huh? You have seen this, na? So this matrix A n minus 1 that I construct with this by just removing this last singular value, so to speak. So the last term in this expansion I just remove. In other words, here I make this sigma n to be equal to 0. And once I make this sigma n to be equal to 0, what is the matrix that I'm remaining? What is the matrix that is remaining? The matrix that is remaining is sigma 1 u1 v1 transpose plus sigma n minus 1 un minus 1 vn minus 1 transpose, right? So this is the matrix that is remaining, and this matrix is the nearest rank n minus 1 matrix to the given matrix A. This is something that you already know. And what is the distance? What is the distance? So A minus A n minus 1. So this distance is sigma n, right? So the distance between the two matrices is sigma n, which is equal to the smallest singular value. So what is this really saying? What is this really saying? It is really saying that the nearest rank deficient matrix to the given matrix A is at a distance sigma n away. Okay, so what is it really saying? Okay, so you think of it really very carefully. Okay, so suppose you have a plane R2. Okay, suppose this is the point. Say this point is, say, P. Okay, then I am saying that I can draw a radius, say for example, radius R. Okay, radius R, circle around point P, and I am saying that all the points inside this circle, have certain property. The first time the property fails to hold true is on the boundary of the circle. The first time the property fails to hold true is on the boundary of this circle. Okay, so that is something important. So this terminology, this idea, I'm going to extrapolate in the space of matrices. In the space of matrices. Okay, I'm going to interpret the same thing here. Okay, so I am given. So suppose this plane, hypothetically, suppose it represents, hypothetically, if this plane is there, it represents matrix set of all n by n matrices. Okay, so this is set of all n by n matrices. Okay, so this is something that you have to understand hypothetically. Okay, just to understand what is really happening. And this is the matrix A that I'm talking of. So this is the matrix A that I'm talking of. Okay, then what is this saying? This result is saying that I will draw a circle of radius sigma n around this point A. I will draw a circle of radius sigma n around this point A. So this is a matrix, and I'll look at interior of this particular circle. So I'm looking at this particular check pattern shaded area, which is inside the circle. What is this result telling? What is this nearest rank n minus 1 matrix to A equal to A n minus 1 telling? It is telling that you have. This is the matrix A that you have. You start perturbing and perturb the entries of A little bit. Where will you reach? You may reach here, you may reach here, you may reach here, here. All these small perturbations will take you to different points which are close to it. So these are all matrices which are kind of A plus delta A, right? A plus delta A type of matrices. The question I am asking is the small perturbation rendering matrix A low rank? So that's what I am saying. So how much perturbation I need to give to matrix A so that it becomes low rank? What is the answer? The answer by this particular theorem, Icart-Young theorem. So this is the Icart-Young theorem, very famous theorem, SVD. So what is this theorem saying? This theorem is saying is that first low rank matrix which is closest to A is on the boundary, So now you understand this particular thing. What is it saying? So if this circle of radius sigma n is really very small, if the circle around this matrix A which is of the radius sigma n is really very small, that means that the smallest singular value of the matrix is really very small. What does that mean? That means that a small perturbation to matrix A may bring you on the boundary. Please remember that it is not necessary that every matrix on the boundary is low rank. It is not necessary. In fact, it is not true at all. There is one matrix setting somewhere here. Which direction, that also I don't know. So this is, say for example, this is the matrix here which is denoted by cross. That's the matrix A n minus 1. Okay, that's the matrix A n minus 1. So if you perturb your matrix little bit, you are close by and you are inside this circle of radius sigma n, then you are guaranteed that this A plus delta A also continues to be a full rank matrix. Do you understand that? Is this point clear? As long as this norm of delta A is less than sigma n strictly, as long as this is going to happen, as long as this norm is strictly less than sigma n, the smallest singular value, do you all agree that A plus delta A is always going to be a full rank matrix? Do you agree? Pratyush?
Yes, sir.
Yeah. So what is desirable? The desirable thing that we may ask for is that this sigma n be as large as possible. So if sigma n is large, then this radius is large. That means this circle is large and the perturbations are better. But if the sigma n is really very small, the other case, then what is going to happen? This circle around A is really very small. That means that A is really very close to losing its full rank property. A is really very close to losing its full rank property. Do you understand that? And how close? It is close by distance sigma n. Is that okay? Do you understand this part? So that's why this sigma n, the smallest singular value, is really very important. It is telling you basically how far away you are from losing the property of full rankness, or in this particular case the matrix is invertible because sigma 1, sigma 2, sigma n are not equal to 0. That means that the rank of matrix A is n. We are talking of n by n matrices. N by n matrices, when they have full rank, what do we know about them? We say that these matrices are invertible matrices, right? So A is an invertible matrix. So we are asking question, what will happen? What is going to happen when you perturb the matrix say only ever so slightly? Will it lose its property of being invertible? Why are we interested? We might be interested because we are solving this problem Ax is equal to b. Now you have A plus delta A, X is equal to B plus delta B. That is the problem really you solve in reality. We have seen this. We have understood the sensitivity analysis. Now when you want to find out X hat, what is the property? A plus delta A should be invertible, right? If A plus delta is invertible, then for any right hand side B plus delta B, you will have a solution. So that's why the invertibility of perturb matrix or the full rank property of the perturb matrix really comes into play, right? So the full rank property will be in terms of least squares problems that we have seen already. So that's why I'm asking this question, and that's why this small perturbation, whether it is making this problem really very good or really very bad, that's the question we are really asking, right? So this is something that is really very important. Another observation I want you to make is the following. Consider a randomly generated n by n matrix. Okay, something very important is randomly generated. So all the n square entries should be generated randomly for this particular matrix. Will this matrix be invertible? If all the entries are randomly generated, okay, all the entries are randomly generated, will the matrix be invertible? Do you understand the question?
Yes, sir, it will be invertible.
It will be invertible. Why do you think it will be invertible?
So because the space of singular matrix is very small, thin line across the n cross n.
So why do you say that it is a very small set? You are right, but why do you say that it is a very small set?
So because for the determinant to be zero, exact conditions has to match, and those
Yeah,
are less probable if they are generated randomly.
yeah, correct. But so determinant equal to zero is a very restrictive condition. That is true. So you are absolutely right. So can anybody have another intuition about this? And this is a very like this is the answer I'm hoping for, but I want other views also. So does anybody have any other things or comments on what Pratyush just said? So what really happens? What really happens is the following. So we are in the space Rn by n. Okay, so this Rn by n is basically Rn square. Okay, n square components are there, so that Rn by n, right? So now consider the case n is equal to 2. Okay, n is equal to 2 also you cannot visualize, but consider the case n is equal to 2, R2 by 2. Okay, so this is the linear space of all 2 by 2 matrices. Okay, so if you consider a 2 by 2 matrix, I'll just write down A, B, C, D. Okay, so these A, B, C, D are the entries which are coming from real numbers. Okay, any real number you can put in place of A, B, C, D, you will get all possible 2 by 2 matrices, right? And when is a matrix invertible? When is the matrix invertible? When determinant is not equal to 0. So when is the matrix singular? When the determinant is equal to 0. So what is the determinant of this matrix? Determinant of this matrix is AD minus BC. And if this is equal to 0, that means that this matrix ABCD is a singular or non-invertible matrix. Okay, singular or non-invertible matrix. Is that okay? So now in R4, suppose you look at this particular vectors, okay, A, B, C, D, or better still, if you put columns one below the other, A, C, B, D, like that. Okay. So you convert this matrix into a four-dimensional set. Four-dimensional set. Then you have vector which is ACBD. And how are you supposed to choose the vector? The vector you are supposed to choose such that AD minus BC. So you take this particular product AD, you take this particular product BC, and this product of AD should be equal to BC. If that product is same, then the matrix, corresponding matrix is not invertible. Otherwise this matrix is invertible, right? So if you choose these four numbers randomly, then the chances are almost zero that these products will be equal to same, like AD will be equal to BC. These products are same. The chances are really very low. Do you all agree? So that set that you are really looking at, so the set that you are really looking at here, in general, n by n, in particular 2 by 2, is really a set which is really very small, right? So hypothetically, once again, if you look at this, this is the space of all n by n matrices. Hypothetically, okay. If this is the set of all n by n matrices, then the set of matrices, which are not invertible, that set possibly looks like this. Okay, something like this. I really don't know how it looks like. Okay, how is the geometry of this set is really a very challenging, important, and not fully solved question in mathematics till today. But roughly it looks like this. So what I am really trying to say is that matrix that you choose randomly, the matrix that you choose arbitrarily, will almost always be an invertible matrix. And the same logic you can extend to the linearly independent columns case when you have a matrix which is Rn by m. Okay, so if you have a matrix of the size Rn by m, then this invertibility you can equivalently say something about columns being linearly independent. We have been doing this a long time. So randomly choose a matrix, you will always see that it is almost always full column rank matrix, or in case of n by n matrices, it is almost always invertible. The other equivalent is that the property of invertibility in case of n by n matrices, or property of full column rank, or what does that mean? Columns being linearly independent in case of n by m, n greater than or equal to m. Okay, that means that you have tall matrices. These properties in language of mathematics are called as generic properties. Okay, these properties are called as generic properties. What is generic property? A property is generic property if the set on which this property does not hold true is a very small set. In terms of mathematics, that set is called as set of measure 0. Okay, so this set does not have, it is not a very big set. It's a very small set. It's the set with measure 0, right? So here, if you see, if you are really looking at a dart, like dart game, and you wanted to put a dart on this particular plane where two red lines are given, and you are supposed to hit a red line, only then you will hit a jackpot. You keep on throwing darts, it's highly unlikely that you will be hitting these lines, right? It's highly unlikely that you will hit the line. So this set, which is like union of two red lines here, that red curves that I have drawn here, so this set is of measure 0, right? So if you are to choose a point randomly, from the plane minus a plane, then the then the point will lie on these two curves, one of these two curves is highly unlikely, right? So that is what is really going to happen. But the important thing to observe here is that if this is the set of all n by n matrices, you may not hit the line, but you may be very close to this line, like here. And the other situation is you are here. So this is a matrix A, and this is a matrix A, and this is some matrix B, let us say, for example. Then matrix B is numerically robust as compared to matrix A. Do you agree? Because a small perturbation in A may render it to be a non-singular matrix. So sigma n here in case of A looks like to be very small, but the nearest place for B to be singular is like really too far away. So so all these matrices here are going to be invertible matrices, whereas here that set of all invertible matrices around A is really very small. So small perturbation might render A to be a singular matrix, but for B to become a singular matrix, you really have to give a very large perturbation. Do you understand? So how far you are from the set of non-invertibility is really the key question to ask here. Because randomly, if you choose any matrix, the matrix is almost always going to be not invertible. The matrix is almost always going to be invertible, or the matrix is always going to be full rank. So the key question to ask is that how far away you are from being losing this property of full rank. Do you understand this? And why is it important? It is important because almost always you will be talking of data. So what will happen? Suppose A is a data matrix. A is a matrix of the size n by 2, right? So you have n rows and 2 columns, n rows and 2 columns. So this same matrix, if you want, you take. So this is height and this is weight, right? And suppose height and weight, I will not really say height and weight, I'll say x and y. Okay, these are the two attributes x and y, and I know theoretically in principle that x is equal to 2 times y. So when I start collecting data, then what do I expect to see? What I really expect to see that the values that are sitting here in column first row x. So this value should be 2 times this value that I see in the column 1, right? So that is what theoretically I am expecting to see. But in real life, what happens while collecting the data, while entering the data into the matrix entries and so on and so forth, there is always some perturbation that goes on in. So even if you started with the exact linear relationship, that means that the rank of matrix A is 1 theoretically, because of the noise present in the data collection methods, measurements, everything that you work with, the matrix that you are looking at here is not A, but you are looking at A plus delta A. So what you had a matrix that was sitting on this set. So A was a low rank matrix. But because of perturbations happening in A became A plus delta A. So you had your matrix A plus delta A sitting over here, which is really very close. When you ask for rank, what is the answer you get? You get it's a full rank matrix. What does that mean? That means that you will conclude that x and y are both the attributes which are really important to describe the whole data. But are they really important? No, in fact, they are linearly redundant to start with. Only the data collection methods, the noise, the measurement noise, etc., are making them look like they are non-redundant, but they basically are linearly redundant attributes. So if you work with only one of them, or if you work with some linear combination of both of them, it's good enough. You don't need two attributes. Only one attribute is enough to work with the data. Do you understand what I'm trying to say here? So the columns are almost linearly dependent. So that's why the question we are asking is not whether the columns are linearly independent or not. How close you are to lose that property? That is the question we are asking. And once we ask that question, what is the answer that we get? The answer that we get is look at the smallest singular value. Based on the smallest singular value, you will realize whether you are very close to this set or you are far away from this particular set. And once you understand how far away, then you take a decision, something like principal component analysis, right? And using PCA, you reduce the dimensionality and you look only with n minus 1 dimensional data. So n minus 1 features are enough because there is almost linear redundancy because your matrix, the data matrix, was very close to this particular cell. Do you understand now, like roughly what is really happening? This is something which is really very involved, and it may take some longer time to digest. But are you at least understanding what I'm saying here? Any comment, any doubt here? Anything that you would like to add? Okay, if there are no comments here at this point of time, I would suggest that let us stop here. And a lot of new things that you heard today in this lecture. So probably it will take some time for you to digest these things. Okay, so I would request you to look into these things once again and try to kind of understand this, and we'll have discussion based on these things once again in next class. If you have any doubts, if you have any comments, your previous experiences to add to this particular discussion, please feel free to do that now or in the next class after you revise all these things once again, and we will continue our discussion from this point in the next subsequent classes. Okay, so if there is nothing else you want to add to, then we can stop here today. Anything?
Sir,
Yes.
sir, can you please share your recorded videos on SVD if you have from previous years?
Okay, I'll find if I have. I'll share.
Okay, sir.
Harshal? Harshal, are you asking a question? Yeah. Can you please repeat? I could not hear you in the first place. Can you? I'm not able to hear. So if it is possible, I could understand little bit of R n square. What?
Can you hear me now?
No. Just a minute. Maybe I will increase the volume at my. Maybe. No, I'm. Can you speak again, Harshal? Harshal, can you ask?
Yes, sir. Am I audible now?
Yeah, yeah.
So my question was that you mentioned that we don't know about the geometry of that space, but won't it be just dimension n square minus 1? Means just a hyperplane would be removed from the n square dimensions.
Yeah, so what really happens is that it may not be hyperplane. It is something which is called as algebraic variety. So what you are really looking at in R4, Rn cross n. So say for example, if you look at R2 by 2, okay. So in R2 by 2, you have this A, B, C, D. Okay. So instead of A, B, C, D, let me use variables. Okay. So X, Y, Z, and W. Suppose these are the entries. Then determinant of this particular matrix X, Y, Z, W equal to 0 is basically XW minus YZ is equal to 0, right? So all the solutions X, Y, Z, W of this particular polynomial equation, that is what I'm really looking at. All the solutions of this polynomial equation. So what you are saying is actually something like a straight flat plane. It is not necessary because you are looking at a polynomial. Basically, this is a polynomial. So determinant becomes a polynomial in four unknowns. What are the four unknowns? X, W, Y, and Z. So it will form a like surface, like weird surface, and that surface is basically called as variety, right? So it will have like dimension which is less. It will not be a solid surface, like solid unit sphere, but it will only be a surface of some shape, which is xw minus yz. So what you are saying is correct, but it not necessarily is a flat surface. So flat surface, if you take, then in R2 it becomes a straight line, right, passing through origin or not, that's okay, but it becomes a straight line. So it may not be a straight line, it can be a curve in R2. So that's what you have to generalize. So
got it, sir. So, but
yeah,
the dimension would be square minus 1, right?
yeah. So dimension would be less, and because the dimension is less, it's almost generic, that it will not have a volume, so to speak, or area, so to speak. So that's why its measure is 0. So it's highly unlikely that you'll pick something from that. So that's why this property is a generic property.
Got it, sir.
Yeah, your observation is right. You have to slightly modify. Basically what you have to say is that you're looking for the algebraic variety, which is nothing but all solutions of this particular polynomial equation xw minus yz is equal to 0. And geometrically, how this set looks for an n by n thing, like what is really the geometric, like is it a like star shaped or something like that, that geometry is not really very well understood yet. So that's what basically is the challenging problem.
Got it, sir.
Yeah. Anything else? Any other comment? Okay, so I hope you understand why this question of asking what is the nearest low rank matrix is very important. It is important because you want to decide with respect to these two red lines, for example, where you are in this set of all invertible or all full rank matrices, right? If you're close, then from data science point of view, what you really think is that the attributes that you have as your columns, there might be an approximate linear redundancy present there. And if you have an approximate linear redundancy present in your linear attributes, then you can kind of remove those attributes, okay, which are bringing in redundancy, and only look at smaller dimensions or less number of attributes. So rather than looking at two attributes here, you will only look at one attribute. That is the idea behind principal component analysis. So principal component analysis basically is helping you to come up with possible linear combinations of attributes. So rather than looking at x, y, you look at alpha x plus beta y, and that alpha x plus beta y actually is the direction which is approximately the column span of this matrix A, right? So that is what this thing is really saying. Okay, so I hope you understand. I hope you understand this part. Okay, so if there are no further comments or doubts at this point of time, we'll stop here today. We'll continue next week. In the next week, we'll focus more onto these low rank approximations and some ways to find these low rank approximations, something called as alternating minimization approach, and some special types of low rank approximations which are called as structured low rank approximations and their applications. Okay, so that is what we will see in the next week. So till then, you revise these things, and if there is anything that you would like to talk about these things in next class, we can definitely discuss. So till then, thank you very much and see you next week.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.